In this lecture, we're going to review a very common method to track frequency of occurrences as a way to describe data and how data are spread out among a number of different scores. And so once again here, when we talk about frequency, we're referring to the number of times a particular score occurs, and the symbol is that lowercase italicized f. And the frequency distribution is just that. It's counting the number of times a score occurs and how those numbers distribute over an organized set. So the important aspect of frequency distributions is that it allows the examination of any unique order or pattern that may arise among a set of scores. In this example, the uppercase N will indicate the total number of scores, and there are four general ways to organize data through the examination of how those data are distributed. The first is referred to as a simple frequency, and then the second method is a relative frequency. The cumulative frequency often accompanies the calculation of the relative frequency, and finally the percentile provides a very useful way to understand how scores rank with respect to each other. And so conditions for frequency distributions must exist. The set of data must be exhaustive. What that means is that there has to be enough categories so that all the observations can fall into place in order to generate a frequency distribution. The data must also be the existence of mutual exclusivity must also exist. In this case, scores or cases cannot be assigned to more than one category. So by being mutually exclusive, the categories are uniquely distinct from each other so that the observations or the individual cases will fall into one and only one category. And so just two examples here in which frequency distributions become very useful when data are nominal or ordinal. And so in these two examples here in these tables here we're simply counting the number of occurrences in each category. So if there are a number of students in a particular class, and if those students are categorized as either male or female, and we would just simply count the number of occurrences. And in this particular case, the tallies indicate that there are 10 males and 10 females, equal number within both of these categories. But oftentimes there are a larger number of categories, and that's where a frequency distribution becomes very unique in providing an overall understanding of how those data will distribute. And so if we have data that are interval or ratio, the simple frequency distribution becomes a very handy way to identify how the scores differ from each other. And once again here, we're counting how many times a particular score occurs. In generating a simple frequency distribution, the researchers have to determine a couple of things. The first item is the number of categories to be created. The second are how wide each of the categories should be. And so therefore there have to be established rules for making a frequency table. And that involves making a score column and immediately to the right making a frequency column, or the number or the tallies of how many times those particular scores occur. And the first step is to collect raw scores. And in this particular example here we see a number of raw scores, and this represents a class quiz. A quiz which was multiple choice that had 17 questions. And we see a wide range of different responses among the students taking this quiz. And so we start by making so the next step, once we've collected the raw scores, we order the scores from high to low. The highest observed score is 17. The lowest observed score in our previous in our raw data was 10. We then start to tally how many students scored 17, how many students scored 16. We see 0 students scored 16, 15, 14, 13, and so on and so forth. Now, once we have the number, we can then generate graphical representations, which makes the interpretation much more meaningful. The first approach that can be taken is by using a bar graph. And the bar graph is oftentimes used when the researchers have nominal or ordinal data, or data that fits within one category. In this particular case, the bar graph, each bar is centered over each score, as you can see here, and the bars do not touch each other. Anytime a graph is generated, the title should be depicted underneath the graph or above the graph as well. And in this case, the title of the graph or the title of the figure should be brief yet descriptive of what the graph is depicting. The second manner in which data can be depicted is through what's called a histogram. And the histogram is basically a bar graph, but in this case the bars actually touch each other. And this is typically used for a small number of scores or scores that fit the interval or ratio description of data. And this would indicate that when the bars touch, this indicates that the data that are collected are on a continuous type of scale and that there are no gaps along the x-axis here. So we see that the outcome measurement, which is the quiz score, is placed along the x-axis. One additional aspect to the histogram is what's called an ogive curve. And the ogive curve is a rather efficient way to determine percentiles and provides a graphical depiction of how the scores accumulate over the course of those different possible outcomes on the quiz. Another method is through what's called the frequency polygon. And this is oftentimes used if there's a large number of interval or ratio scores. And in such case, the data are often continuous in nature. So in this example, we see the same data from the quiz scores, but this time the frequency polygon is used to depict the pattern that emerges from those scores. The next step is to calculate the relative frequency, and what we're calculating here is a proportion of the total number of scores that's made up by a score's simple frequency. And it's basically a fraction of the total sample size. And this tends to, the approach here is to group the relative frequency distribution. The same rules do apply as depicted on the previous slide for the simple frequency. Following the calculation of the relative frequency, which is a proportion, the cumulative frequency is then calculated, which according to the term starts to accumulate the number of the scores that occur at or below a particular score, and that moves us to the computation of the percentile. And the percentile is a percent value at which a particular score resides, and all the rest of the data lies below that particular score. So in this frequency table, here we see our original scores. The top score on the quiz is a 17. That's the highest possible score that could be attained. And the lowest observed score was 10. And the next column to the right is just simply a tally of how many students scored 17, how many students scored 16. We see that 4 students scored 15, so on and so forth. The relative frequency, based upon the equation on the previous slide, is a ratio expression of 1 divided by the total sample size, and here we see 0 divided by the total sample size, and this continues all the way down to the bottom of the table, which we'll describe here shortly. The next column is the cumulative frequency, which we actually start to count from the bottom of the table upwards. And then the last column to the right is the percentile, or the percent at which a particular score resides, and all the other scores that reside below that particular score. So if we focus here on we come back to the frequency column, the raw numbers. If we add up all of these numbers, it should equal the total sample size. The total sample size in this case were 18 students. And we notice that if we skip a column and go to the cumulative frequency, as we move upwards with the table, we start to add the number of students as we go higher and higher on the possible scores. And so we start with the first row on the bottom with the lowest score of 10. Only 1 student obtained that score, and the relative frequency was 0.056, 1 divided by 18, and we see that the cumulative frequency would be a 1, so it would be the exact same number we see in this cell right here. We then add this number to the next frequency number, and we place that number over in the next cell above the cumulative frequency cell from the score of 10 out of 17. And so what we see here is that because we've added 1 more student, the cumulative frequency is a 2. We repeat the same process where we add 2 to 1, and that will give us 3 total scores that have accumulated at this point, and we see that we have 1 plus 1 plus 1, 3 students scored at 12 or below. And then this would continue all the way up to the top of the table, where the final value for the cumulative frequency should equal the value in the cell below at the very bottom of the frequency table, or the frequency column. The relative frequency values should also equal 1.0. In this particular case, we see that it equals 1.001, but this is attributed to a rounding error. For the percentile column, we see that the highest score of 17 resides at the 100th percentile, indicating that 100% of all the scores will lie at this value and below. So we would say that this 1 student sits at the 100th percentile in terms of this student's quiz performance. So this ends this lecture on graphing frequency distributions.